In this session, we're going to evaluate entries in the expert system of Tetracorder and compare the continuum remove spectra and the continuum endpoints that define spectral features. I have two windows open, and we'll see where I've placed the location. So this is the Cuprite mapping directory that we did in an earlier video. And there are two things that are important here. The SpecPR restart file. So I'm going to run SpecPR. So I'm going to execute this command. So the restart file, graphics terminal, and suppress messages, although this time I'm not going to suppress messages. And it shows me recent additions. And in 2018, we can enter Tetracorder spectral features here, like this one, and plot them on a SpecPR plot. This file here is located in the source code directory and dSpecPR is the developmental. dSpec notes shows this file. Okay. So I've started SpecPR. Now the other file that's important is the Tetracorder expert system, and that's this file right here. So we're going to view that. We're not going to change it. We're just going to look at it. And I've started it up. Normally it would start here. And I'm going to search for alunite as an example. And let's get past the comments. And this one, we can compare that one. I like this one. We'll put this where we can see the entries and also see our plot. So I'm going to go to the plot routine, and the record number here is 294, and SPLib06 is S06 is the convolved Cuprite Avarice 95 convolved library, so that'll be Y. So Y294 will show this spectrum, and change the scale, auto scale. So we see a lot of spectral features here. This is a classic alunite spectrum. We also have, we're going to look at another spectrum, and let's go down and bring up the next spectrum. That one's also a K alunite. Let's go down one more to this sodium alunite, and we'll plot that spectrum. And notice the spectral features are different. We can plot both of them. O means overlay. So we're going to plot spectrum in record 288 and 294 overlaid. So that's the first spectrum and the second spectrum. So now we see they're different. We can also see that the wavelength positions are different, more so here than here. And that's a good reason why we should be using two spectral features to identify what kind of alunite this is. So there's another way to do this. Let me just bring up Y294, and there's another way to look at spectral features. And if we read the menu over here, we'll see in capital A does a band analysis. If we want to change scale, we can do that here, but I'm going to leave it as is, and then just go into a little a. Then we click our 2 continuum points that we want, press return, and each step we press return, press return, press return. And so we see the band center is at 2.1757 with a width of 0.0935, depth of 25%, and an asymmetry of 1.3. So we could program all of that in to here, but we need to know what the continuum points are, and we'd have to decide whether adding a asymmetry parameter, which gets expressed. We don't have asymmetry per se, but because the whole feature is fit, the feature fit, it inherently does the asymmetry. If we needed shoulderness, then we'd have things here that would help us define the shoulderness. See the shoulderness line. In this case, we don't need that. And that's a decision that you get with experience on what we're trying to distinguish between other things. And in a later session, we'll do shoulderness. So this is fine, but that's not the information we need. So what we want to do in this session is compare the features defined in Tetracorder here, and this spectrum is 294, so let's go up to 294. So back to the main menu of the plot, we can define spectral features via that the information in the messages for new features. TF1 is Tetracorder feature 1 equals, and we need a keyword. We'll call it K alunite, and then this information. Now if we press return, we'll see that's what Tetracorder is doing for this feature. So let's define TF2, K alunite, and that would be this feature. So we have the 1.5 feature and the 2.17 feature. Now, how is that different than the other spectrum? So if we go down to the next spectrum, the sodium alunite, we can bring that up as an overlay. V1 equals, that'd be Y288. That's the 288, and the spectral library 06 is assigned to Y, and the wavelengths are capital Y6. And that'll always be the case, and that's given right down here. For convolved spectral libraries that are in the small category less than 2171 channels that we learned about in a previous video, the wavelengths are always put in record 6. So you don't have to look it up. If you didn't remember that, you'd have to do a listing of the file and find the wavelengths. So there's the the sodium alunite in red, and you can see the band's shape is different. Now if we go back and do our band analysis, capital A, lowercase a, then basically reproduce what Tetracorder is doing. And there's the continuum removed features compared. And you see that the band has a different width and has shifted for the red spectrum. That's the sodium alunite. We can get out of that, and we can go and do the other spectrum, or the other spectral feature, I should say. And you see there we have a considerable shift. Now, this is pretty small, so let's go back and zoom in on this. We can zoom in with the capital S function. Let's do there to there, for example. Now, go back to our band analysis. And I'm going to choose this point here. It's a single point in this routine. So you see, but when Tetracorder works, it's going to work over an interval and get a better average. But here we can see there's a definitive spectral shift. And Tetracorder is keying in on that shift to distinguish sodium alunite from potassium alunite. Let's change our scale back 1.3 to 2.5. Okay, it's that simple. So for defining where a continuum goes, there's also in SpecPR G for graphics cursor read, and you can move along here, and two parameters are given. One, the nearest channel, and the other one is the XY position of the cursor when you clicked. Let's, and right click gets you out of this mode. Let's zoom in on this feature. And let's redefine both of these features to be auto-scaled. So this is Y288, capital Y6. So OV1 equals Y288, Y6, and auto-scale. Now it's auto-scaled. And if we change the other scale to auto-scale, then they're close. Now the spectra are different, so the auto-scaling is different. But it gets you close, so you can see there's a wavelength shift. And this helps you choose continuum points. You might ask why the continuum is over here versus over here, and whoever put these features into Tetracorder made that choice. Over here might actually be a better choice. That would have to be something that would be evaluated. We know this works well. And then another situation in terms of choosing the continuum points, let's go to the other wavelength. And here, the continuum point was chosen here, whereas you might think it would be better over here, but we're pushing limits on atmospheric transmission. As we go to shorter wavelengths, we're getting into a strong terrestrial water band that in many locations the water in the atmosphere is enough to make these shorter wavelengths opaque so we don't get any signal. This is a wavelength where average data gets corrected well enough with the radiative transfer models that we can be confident in defining this absorption band position. You can see with the sodium alunite that the wavelength position would be over here, so let's go ahead and add that one in. TF3 equals, but it's only going to do it on this feature. We need to actually X out of here and bring up Y288. and change TF2. So when Tetracorder is comparing the potassium alunite to this spectrum, it's using this continuum, and you see it's not going to see much of a band at all. So let's redefine TF2 to be what Tetracorder would do for sodium alunite. And that's the continuum that it uses. So you can use this tool to explore how Tetracorder would respond to different spectra. You can throw different spectra for a given continuum and see how it would do. And in this case, I think it's doing pretty well. I wouldn't change anything here. And we know from working at Coopright and Greg Swayze's thesis that the alunite identifications are really quite good. And with that, we'll stop this session.